Trajectory improvement and reward learning from comparative language feedback. The problem we focus on is reward learning, where the robot learns the reward function of a user. One common solution is comparison feedback, where a human user chooses their preference from two trajectories. Then, the robot learns the reward function from this feedback. However, this is time-consuming as user needs to look at both trajectories to give feedback, and each feedback provides at most one bit of information. As an alternative, we propose to use comparative language feedback. The user only had to look at one trajectory to give the feedback, like, move closer to the cube. This is more time-efficient to give feedback, and language feedback is more informative than the comparison feedback. To utilize comparative language feedback for reward learning, our approach consists of two stages. In the first stage, we learn a shared latent space for trajectory and language feedback. Then, in the second stage, we leverage the learned latent space to learn users' reward functions. Our training data consists of trajectory pairs and corresponding language feedback that depicts their difference in one feature. To learn the shared latent space of language and trajectory, we have a neural network trajectory encoder and a pre-trained T5 model. We then align the difference of the trajectories with the language feedback. Next, we have our architecture for human reward learning. In each iteration, we randomly select one trajectory for the user to give language feedback on. Using the frozen encoder and T5 model, we get our embeddings, which are used to create an improved trajectory and learn the user's reward function. To test the effectiveness of our framework, we conducted simulation experiments in RoboSuite and MetaWorld and user studies on the real Widow X robot. Our first experiment is iterative trajectory improvement. A user gives language feedback to iteratively improve a trajectory until they're satisfied. In simulation, we're able to improve the trajectory until near optimal. In user studies, we found high average scores across experience, speed, and satisfaction, and most users being satisfied with the trajectory after 3 to 5 iterations. The second experiment is comparing reward learning between our approach of language feedback and the common approach of pairwise comparisons. For the simulation environments, we found favorable results when measuring cross-entropy and the true reward values of the calculated optimal trajectory. In user studies, users are shown random trajectories and give feedback. Then they're shown the optimal trajectory given the learned reward function every 5 iterations. We also found favorable results, with users preferring our language method over the comparison method for experience, speed, adaptation, trust, time efficiency, and adaptability. In summary, we proposed a framework that improves robot trajectories and learns a reward function with language feedback, and we found our approach outperformed comparison preference learning. Thank you.